Hi students, welcome to our physics channel Physics Star. Today we will discuss uh, two different problems which are given in a book. Those are related to speed of a transverse wave in a string. Now let us try to do these problems. So let us see the first one. A uniform rope of mass m and length L hangs from a ceiling. Calculate the speed of transverse wave in the rope at a distance x from the lower end. Also, calculate the time taken by the transverse wave to travel the full length of the rope. See, we need to take the rope. It is a massive rope and it is fixed to one end and it is hanging freely. It is just hanging from one fixed end. Now we need to find out, suppose if a wave is generated from the bottom or if a pulse is generated from the bottom, how with how much speed it goes to up, as well as what time does it take to move from lower end to upper end, right? So for that purpose, first let us try to draw the diagram. Let us try to draw the diagram for first one A. There are two questions here. Now I am solving the first one. In that, actually there is a rope. See, this is a fixed end. Now I am taking a rope here. Here is a rope. And this rope has certain length actually. This rope has a certain length L, and in that one pulse is generated like this. In this one pulse is generated like this. From the bottom one pulse is generated. Now when it is at a certain distance x from the lower end, if we want to calculate, now let us suppose this pulse is at a distance x from the lower end, or else let us take at any distance. Now suppose if it goes up with certain velocity, now what we are doing, we are just giving a jerk at the lower end of the rope. Because of that one pulse is generated and that pulse is going up. Okay now. So while the pulse is going up with certain velocity, now what am I going to take? I am going to find out the tensional force acting on that pulse, first of all, on that element of that pulse. Now consider this is an element which is inside the pulse, means at this point, at the peak value of it, peak point of it. Okay now, I am taking an element, and on that element, consider this is that element. On this element, how much amount of tension exists? From that element onwards, the distance is x. Am I right or not? So now let us consider the tensional force first of all. Because if you want to find the velocity, formula is what? Root of t by mu, right? So first tensional force T is equal to the total length from the bottom. The total rope is there, no? Below x. Total x length is there, no? The total mass of that rope, that x part of that rope, is exerting the tension at that point, at this point. Yes or no? Okay now. So the total x length of the rope is exerting the tension because of its weight, right? So that's why what am I doing? I am just finding out the tension of that particular mass of the rope, right? So therefore consider it is m dash. Total mass is m. Let us consider total length is L. Total length is L. So now this mass I am considering m dash. So now I am finding out m dash into g. This is tensional force. Now what is m dash here? M dash is equal to mass is equal to density into length, right? So density I am taking mu into length value I am taking x into g. This is tensional force. See, this is T, which is equal to mu into x into g. Okay, now that much of tension will be exerted at point P in that entire row, at this point P. Now let me draw that point P, this one. This is that point P. Okay. Now what is now how to find the velocity now? Therefore v is equal to speed of the wave. Let us find speed of the wave now. Therefore speed of wave or a pulse, whatever it may be, v is equal to root of t by mu. What is that value? Root of t value mu xg divided by mu, right? Therefore mu gets cancelled, hence v is equal to root of xg. Here actually mu is a linear mass density of the rope. Initially in other chapters we may consider the linear mass density as lambda, but here it is not like that. Okay, now lambda means we may get confused that it may be wavelength, right? That's why I am taking instead of lambda mu. Okay, so now we have got the velocity value. This is velocity value, v is equal to root of gx. Now with this velocity, how much time does it take to go from the lower end to the upper end? The total pulse will go from lower end to upper end, and how much time does it take for that? Now this velocity, let us write that velocity as dx by dt is equal to root of xg. Now taking x values separately and t values separately, we can get, okay, 1 by root x into dx. Send this dt to this side, root g into dt. As g is a constant value, therefore I am taking it outside the integration while integrating. Okay, now let us integrate this. Integration of 1 by root x dx is equal to integration of, now taking root g outside, root g into integration of dt. Now limits are from 0 to L. Total length, no, it is traveling through total length of the rope, right? So, and it is from 0 to t. So we can get 1 by root x. Integration means it is 2 root x. Limits are 0 to L is equal to root g into t. Now in order to find out the time taken, let us find the time taken here. Therefore time taken by the pulse to go from lower end to upper end. How much time does it take now? So therefore t is equal to 2 into, instead of x, first we need to substitute L, later 0 substitute, then it doesn't make any difference, right? So 2 root L divided by root g. Therefore let us write it clearly. T is equal to 2 into root of L by g. This is a time taken by the pulse to go from the lower end to upper end when a rope of certain mass is hanged from a fixed end. Okay, na? This is the time taken. T is equal to root of 2 into root of L by g. Okay. Now let us discuss the next problem. It is quite easy and it is also similar problem. That's why I am discussing here. A wire of variable mass. Let us see the second one. A wire of variable mass per unit length, mu is equal to mu naught into x. Here in question A, mu is constant. It is a uniform rope. Means throughout the rope density will be same. But here in question B it is not like that. Mu is equal to mu naught into x. It means that it is density is changing according to x. X means length of the rope. So mu is equal to mu naught into x is hanging from the ceiling as shown in the figure. The length of wire is L naught. A small transverse disturbance is produced at the lower end. Find the time after which the disturbance will reach to the other ends. Means same situation, but only one is different. What is that? Linear mass density is varying now. But before in the question A, it is not varying, it is constant, but now it is varying. So in the case of varying linear mass density, how to find that same answer? Time taken. Let us assume this is a fixed end. Now consider this is a rope. Now assume that here a certain pulse is generated in this rope at a distance x from it. Now mass density is different. Now let us take time first tensional force exactly at this point. Let us find out the first tensional force. What is the tension here? T is equal to tension at point P. What is the remaining length? Remaining length is actually, we can't take it as directly m into g. Yes or no? Due to its weight. M value we need to consider it as mu into taking an elementary length in that entire rope. Okay, elementary length is a dx into, so this is entirely means dm. The meaning of this entirely, mu into dx is nothing but dm. T is called mg actually. That m value I am writing now, dm value into g. Now what am I doing? I am just taking one elementary portion because it is not constant. Density is not constant throughout that. That's why I am taking dm value here. And that dm value not exactly there. Where we are taking the point P, there we are considering the element. See, I am taking that element here. See, this is that element dm value. Now we are finding out for that value. Okay, so listen. So this is dm value. Now what is mu value? In the question it is given that mu is equal to mu naught into x, right? Mu is equal to mu naught into x. So now mu is equal to mu naught into x into dx into g. Assume this is dt. Very small tension is there, is existing in that particular element dx. Okay na? So therefore now if we want to get the total tension, T is equal to integration of mu naught g into x dx. Now let us take that mu naught g outside. So mu naught g into integration of x dx. What is its value? Therefore tensional force is equal to mu naught into g into x square by 2. Limits, applying the limits to this 0 to L. Okay, now or else you may take there only. I'm sorry, no need of taking that 0 to L. No need of taking that limits, because there only we are calculating at a particular distance x from the lower end. So now we need to find the speed of this pulse. So v is equal to root of t by mu. So root t value mu naught g x square by 2 divided by, here mu is nothing but what, again mu naught into x, right? So mu naught gets cancelled, and finally we are going to get root of gx by 2. This is velocity, or this is the speed of a transverse wave in that string, where density is changing as mu is equal to mu naught into x. See, this is v. This is v value. Now we are finding out the time taken. How much time does it take to reach to the top? How much time does it take to reach the top? So for that, time taken by the pulse to reach the top, time taken by the pulse to reach the top, okay, top of the rope. So how to find the time taken? Instead of v, I am writing it as dx by dt, which is equal to root of gx by 2. Therefore, now sending this root x to this side, 1 by root x dx is equal to root of g by 2 into dt. Yes or no? Now integrating on both sides. And now let us apply the limits, because it is crossing the entire length of the rope, right? So 0 to L. Okay, now. So 1 by root x dx means what? 2 root x. 2 root x, limits are from 0 to L, which is equal to root of g by 2 into t. Okay, because integration of dt is t. So 2 into root L is equal to root of g by 2 into t. Therefore, we are going to find out the time. In this situation, t is equal to 2 root 2 into root of L by g. See, this is simply written as root of 2 root 2 means what? 8. Root 8 can I write? So root 8 L by g. So what is the time taken? Time taken is root 8 L by g in this case. So here I have discussed two different situations. One is a rope, a massive rope. Okay, a massive rope which is hanged freely from a fixed end. Okay, now when a jerk is given at the bottom, a pulse is generated and it goes up with certain velocity. Now we are finding out how much time does it take to reach the top of it. So how much time does it take? In the previous question we got it as t is equal to 2 into root L by g, and the speed of it is v is equal to root xg. And in the second question, we have taken variable density, like density is not constant here. Okay, now, and mu is given as, and that variable density is given as mu is equal to mu naught into x, linear mass density. Mu is equal to mu naught into x. If there is a variable density in the rope, then how to calculate the time taken? This is the situation. This is a time taken. See, v is equal to root of gx by 2, and the other one is t is equal to root of 8 L by g. Okay. This is about the two problems which are based on speed of wave or speed of transverse wave in a string. So keep watching my channel. Please do like, share and subscribe to my channel so that you can get still more number of problems with conceptual understanding. Thank you.